Hello and welcome. Tonight we're going on a journey through one of the most beautiful mysteries in all of science, a mystery that lives in every moment, in every heartbeat, in every tick of the clock, beside your bed. Picture this, October 1971. Two physicists board commercial airplanes, each carrying something extraordinary: atomic clocks, the most precise timepieces humanity had ever created. One physicist flies eastward chasing the sun. The other flies westward racing away from it. When they land and compare their clocks to an identical one that stayed on the ground, they discover something that sounds impossible. The clocks no longer agree. Time itself, measured to the billionth of a second, had moved differently for each of them. The flying clocks had aged differently than the one that stayed behind. This wasn't a malfunction. This was proof that time is not what we thought it was. If you're curious about the hidden nature of reality, about how the universe works in ways that challenge everything we assume, then stay with me tonight. And if you enjoy falling asleep to stories that expand your understanding of existence, please like this video and subscribe. It helps us create more journeys like this one, and it means the world to us. That experiment in 1971, known as the Haffel-Keating experiment, named after the two physicists who conducted it, wasn't just a scientific curiosity. It was a revolution wrapped in a suitcase. Joseph Haffel and Richard Keating were testing one of the strangest predictions ever made by human thought, that time does not flow at the same rate everywhere. That depending on how fast you're moving or how deep you are in a gravitational field, your clock and your aging and every process in your body could be ticking at a different speed than someone else's. They booked tickets on regular commercial flights. Haffel went eastward, flying around the world with the Earth's rotation. Keating went westward against it. Each carried cesium atomic clocks devices so precise they lose only 1 second every 100 million years. These weren't wristwatches. These were instruments that could measure time's passage to within nanoseconds, billionths of a second. When they returned and placed their clocks next to the reference clock that had remained at the Naval Observatory in Washington, the results were undeniable. The eastward flying clock had lost about 59 nanoseconds. The westward flying clock had gained about 273 nanoseconds. Time had literally moved at different speeds. Now you might be thinking, nanoseconds? That's nothing. That's less than a blink, less than a breath. Why does this matter? Here's why. This tiny difference, this proof that time is flexible, is the only reason your phone can tell you where you are. Every day you rely on something that would be impossible if time were absolute. The Global Positioning System, GPS, depends entirely on satellites that are experiencing time differently than you are. Those satellites orbit about 12,500 miles above Earth, moving at around 8,700 miles per hour. Up there, two things happen. First, because they're moving so fast, their clocks run slightly slower than clocks on the ground, about 7 microseconds slower per day. This is velocity time dilation, the effect that comes from speed. Second, because they're farther from Earth's gravitational pull, their clocks run faster than clocks on the ground, about 45 microseconds faster per day. This is gravitational time dilation, the effect that comes from gravity's weakening grip, the total effect. The satellite clocks run about 38 microseconds fast every single day. That might still sound small, but light travels about 1 foot per nanosecond. In 38 microseconds, light travels about 38,000 feet, more than 7 miles. If the GPS system didn't account for these time differences, if it didn't constantly correct for the fact that time moves differently up there than down here, your position would drift by more than 6 miles every day. Within a week, your GPS would be useless. Your map would show you in the wrong city, all because time is not the rigid universal thing we imagine it to be. This is what Einstein understood. In 1905, he published his theory of special relativity, which revealed that time is woven together with space into a single fabric space-time, and that motion through space affects motion through time. Then, in 1915, he went further. His general theory of relativity showed that gravity isn't just a force pulling objects together. Gravity is the warping of space-time itself, Mass, anything with weight, bends the fabric of space and time around it. And where space-time is bent, time flows differently. Think of it like this. Imagine space-time as a vast trampoline stretched flat. Now, place a bowling ball in the center. The trampoline sags under the weight. That sag is gravity. A marble rolled across the trampoline will curve toward the bowling ball, not because the ball is pulling it with some invisible force, but because the trampoline itself is curved. The marble is just following the shape of the surface. That's what gravity is, a curvature. And just as the surface curves through space, it curves through time. Near the bowling ball, where the sag is deepest, time moves more slowly. Farther away, where the surface is flatter, time moves more quickly. You live at the bottom of such a sag, Earth's gravitational well. Every second of your life, you are experiencing time more slowly than someone floating freely in deep space, far from any star or planet. It's not that your clocks are broken. It's that time itself is stretched by the mass of the Earth beneath you. This isn't philosophy, it's measurement. Atomic clocks placed at different altitudes, one at sea level, one on a mountain, tick at measurably different rates. The higher clock farther from Earth's center runs faster. Time on top of Mount Everest passes about 30 microseconds faster per year than time at sea level. Over a lifetime, the difference is still tiny, just milliseconds. But it's real, it's been measured, it's been confirmed over and over again. And this matters far beyond clocks. This is about the nature of reality. We walk through life assuming that time is universal, that when 1 hour passes for me, 1 hour passes for you, for everyone everywhere. But that's not true. Time is local, it's personal. It depends on where you are and how you're moving. The now you experience this very moment is not the same now someone on the International Space Station is experiencing. Not exactly. Their now is slightly ahead of yours. They are, in a very real sense, living a fraction of a second in your future. This is why the Havlik-Keating experiment was so profound. It took Einstein's mathematics, these elegant equations describing the relationship between motion, gravity, and time, and turned them into something you could hold in your hands. 2 clocks, 2 airplanes, proof that time bends. Have you ever wondered if the time you experience is the same as the time someone else experiences? Not in a poetic sense, but literally. The answer is no, it isn't. And now you know why. Before 1971, Einstein's theories had been tested in indirect ways by observing starlight bending around the sun, by measuring the orbit of Mercury. But no one had taken a clock, moved it around the Earth, and directly shown that time had changed. Havlik and Keating did that. They spent less than $10,000 on plane tickets and proved one of the most mind-bending truths in all of physics. Their experiment was published in the journal Science, and it sent ripples through the scientific world. Not because anyone doubted Einstein, but because now the abstract had become tangible. Time dilation wasn't just theory anymore. It was something you could pack in a suitcase and take on a flight. And once that door opened, everything changed. Scientists realized that if time could be measured bending under everyday conditions, on commercial flights at different altitudes, then we needed to rethink how we synchronize the world. Banks, stock markets, telecommunications, navigation. All of these systems depend on precise timekeeping. And if time runs differently at different places, then we need to account for that. We need to understand not just where we are, but when we are. This is the world Einstein gave us. A world where time is not a river flowing at the same rate everywhere, but a landscape rising and falling, speeding and slowing, depending on the gravity beneath you and the speed you carry. A world where 2 twins can age at different rates, where astronauts return from space younger than they would have been if they'd stayed home, where the clock in your hand and the clock on a satellite overhead are living in slightly different streams of time. It sounds like science fiction, but it's science fact. And it's only the beginning, because now we understand that time is flexible, we can start to ask deeper questions. How much can time slow down? What happens to time near the most extreme objects in the universe, near black holes, where gravity is so strong that space-time is twisted into knots? What does this mean for the future of humanity? For space travel, for the possibility of journeying to distant stars? The clock that changed everything didn't just prove Einstein right. It opened a door to understanding the universe in a completely new way. And as we move forward, you'll see just how strange and how beautiful the truth about time really is. Now that we've seen how moving clocks reveal time's hidden nature, let's go deeper. Let's explore the force that rules time's flow on Earth and discover why every moment of your life is shaped by an invisible hand that reaches down from the stars themselves. Imagine standing at the base of a mountain looking up. You and a friend synchronize your watches perfectly matched down to the millisecond. Your friend climbs to the summit while you stay below. When they return a year later, their watch shows a different time than yours, not because of a malfunction, but because they lived higher, farther from Earth's core, where time itself runs faster. They aged more. They experienced more seconds, more heartbeats. Gravity didn't just hold you down, it held your time back. This is the invisible architecture of reality. Gravity doesn't just pull objects, it shapes when things happen. And the deeper you are in its grip, the slower your clock ticks. This is gravitational time dilation, and it's happening to you right now. You've been inside Earth's gravitational well your entire life. Every moment you've experienced has been stretched ever so slightly by the mass of the planet beneath your feet. If someone were floating in the vast emptiness of intergalactic space far from any star or galaxy, their time would flow faster than yours, not by much fractions of a second over a lifetime, but measurably, undeniably faster. You are living in slow motion compared to the universe at large, and you never even knew it. Let's understand how this works. Einstein's general theory of relativity tells us that mass warps space-time. Picture a heavy object placed on a stretched rubber sheet. The sheet sags. The heavier the object, the deeper the sag. Now imagine that sheet isn't just space, it's space-time, the four-dimensional fabric where space and time are interwoven. When mass creates a dip in this fabric, it doesn't just curve paths through space, it curves paths through time. Near massive objects, time moves more slowly. This is not metaphor, this is geometry. This is the structure of the universe. Here's a concrete example. The International Space Station orbits about 250 miles above Earth. Up there, astronauts are still within Earth's gravitational influence, but they're farther from the planet's center than we are. Because of that, time runs slightly faster for them, about 0.01 seconds, faster per year compared to someone on Earth's surface. It's tiny, yes, but measurable. Now, consider someone standing at sea level versus someone standing atop Mount Everest, which rises 29,032 feet above sea level. The person on Everest is farther from Earth's center of mass. Gravity's pull is weaker there just slightly, but enough. Time at the summit runs faster by about 30 microseconds per year. If you spent your entire 80-year life on Everest's peak, you would age roughly 2.4 milliseconds more than someone who lived their whole life at sea level. You would have lived more time. Now scale this up. Go farther from Earth. The moon orbits about 240,000 miles away. Clocks on the moon tick faster than clocks on Earth by about 56 microseconds per day. That might not sound like much, but NASA is already planning for it. As humanity prepares to return to the moon and establish permanent bases, we need to create a lunar time standard. Why? Because if astronauts on the moon and mission control on Earth don't account for this difference, navigation systems will fail, communications will desynchronize, experiments will be compromised. Time itself must be translated between worlds. Think about what this means. When humans live on the moon, their clocks and their lives will be running in a slightly different time stream than ours. After a year on the lunar surface, an astronaut's clock will have gained about 20 milliseconds compared to an identical clock on Earth. It's not science fiction, it's logistics. NASA and the European Space Agency are right now developing timekeeping systems that can handle these differences. They're building what's called a cislunar time standard, a unified way to measure time across the Earth-Moon system. Because in the future, when spacecraft are constantly traveling between worlds, everyone needs to agree on when things happen. Let's go deeper still. Gravitational time dilation isn't just about altitude. It's about how close you are to the center of mass. Earth's gravity creates what physicists call a gravitational well, a region where space-time is curved inward like a funnel. The deeper you are in the well, the slower time flows. At Earth's surface, you're deep in the well. At the moon's orbit, you're higher up, closer to the rim. In the vast space between galaxies, you're essentially out of the well, entirely on flat ground, where time runs at its maximum rate. Here's where it gets beautiful. Every massive object in the universe creates its own well. The Sun, for instance, is vastly more massive than Earth, about 333,000 times more massive. Its gravitational well is correspondingly deeper. If you could stand on the Sun's surface hypothetically, since it has no solid surface and would instantly incinerate you, time would run noticeably slower than on Earth. Calculations show that clocks on the Sun's surface would lose about 66 seconds per year compared to clocks in deep space. The Sun's mass warps space-time so intensely that time itself bends. But even the Sun is nothing compared to the most extreme objects. Consider a white dwarf, the collapsed core of a dead star about the size of Earth, but with half the mass of the Sun packed into that tiny volume. Gravity on a white dwarf's surface is about 100,000 times stronger than Earth's. Time there runs significantly slower. If you watched a clock on a white dwarf from a safe distance in space, you'd see it ticking noticeably slow, like a film played in slow motion. A person standing on a white dwarf, if they could somehow survive the crushing gravity, would age more slowly than you. Their heartbeat, their thoughts, the decay of atoms in their body, all of it would unfold in stretched time. Now, here's something most people get wrong. They think gravitational time dilation is about feeling different or about clocks malfunctioning. It's not. If you were standing on that white dwarf, you wouldn't feel time moving slowly. To you, everything would seem normal. Your heartbeat would feel regular. Your watch would tick once per second just as always. It's only when you compare your time to someone else's, someone farther from the mass, that the difference appears. Time dilation isn't something you experience subjectively. It's something that's revealed through comparison. This is why Einstein's theories are so profound. They don't just describe time as something that changes. They reveal that time has no absolute meaning. There is no universal clock. There is no cosmic metronome ticking away the same seconds for everyone everywhere. Instead, every observer, every location, every trajectory through space-time has its own time. Your time is defined by your path through the gravitational landscape of the universe. Move to a different location, and you move to a different stream of time. Let's consider another example that brings this home. GPS satellites orbit at about 12,500 miles altitude, where gravity is weaker than at Earth's surface. Because of this weaker gravity, time on those satellites runs faster, about 45 microseconds per day faster. We talked earlier about how their speed also affects time, slowing it down by 7 microseconds per day. When you combine both effects, gravity speeding it up, velocity slowing it down, the net result is that satellite clocks run 38 microseconds fast per day. Engineers program the satellites to tick at a slightly slower rate before launch, so that once they're in orbit, their clocks synchronize with ours. They deliberately build in a time dilation correction. What if we didn't do that? What if we ignored gravitational time dilation and just assumed time was the same everywhere? Within 2 minutes, your GPS location would be off by about a mile. Within a day, it would be off by more than 6 miles. The system would be useless. Every autonomous car, every airplane, every ship navigating by GPS would be lost. The fact that GPS works the fact that you can find your way home using a device in your pocket is direct everyday proof that gravity bends time. Have you ever stopped to think about how strange this is? That the ground beneath you is actively slowing down your clock, that by simply existing on Earth's surface, You're experiencing less time than someone floating freely in space. This isn't just abstract physics. It has implications for the future of humanity. As we venture into space, not just visiting, but living on other worlds, we'll be stepping into different gravitational wells. On Mars, which is less massive than Earth, gravity is weaker. Time on Mars runs slightly faster than on Earth, by about 0.3 milliseconds per day. Over a year, that's about 100 milliseconds. Martian settlers will age faster than people on Earth. Not by much, but measurably. If someone spends 20 years on Mars and then returns to Earth, they'll have aged about 2 seconds more than if they'd stayed home. Their twin on Earth will be 2 seconds younger. It sounds trivial until you remember that this is time itself we're talking about. This isn't just clocks. This is the rate at which particles decay, the speed at which chemical reactions occur, the pace at which life unfolds. A Martian day isn't just a different number of hours because Mars rotates differently. It's a different flow of time because Mars bends space-time differently. The gravitational well isn't just a scientific curiosity. It's the architecture that defines when things happen. It's why time on a mountaintop is different from time in a valley. It's why astronauts return from space having aged less than they would have on Earth. It's why the universe doesn't have a single unified now, but instead has countless nows, each one local to its position in the gravitational landscape. And here's the beautiful part. This isn't hidden from us. It's not locked away in distant galaxies or inaccessible dimensions. It's right here all around us, quietly shaping every second we live. The mass of the Earth, the mass of the Sun, the mass of the galaxy. All of it reaches out through space-time, bending the flow of time, creating an invisible topology of faster and slower, earlier and later. We navigate this landscape every day without realizing it, but now you know. Now you can see the invisible hand that's been guiding your clock your entire life. This is the power of gravity, not just to pull, but to shape time itself. And as we'll see next, when you add motion to this equation, when you combine the warping of gravity with the stretching of speed, something even stranger emerges. Something that challenges the very notion of what it means to exist in the same moment as someone else. Imagine two identical twins born on the same day sharing the same DNA, the same heartbeat at birth. One stays on Earth. The other boards a spacecraft and accelerates to nearly the speed of light, journeying to a distant star and back. When the traveling twin returns, they step off the ship and they're younger. Not metaphorically, not psychologically, biologically, physically, measurably younger. Their cells have divided fewer times. Their heart has beaten fewer times. They have lived through fewer seconds. How is this possible? This is the twin paradox, one of the most famous thought experiments in physics. And it's not a paradox at all, it's a prediction. A prediction that has been tested, confirmed, and is happening right now to astronauts orbiting above us. We've explored how gravity slows time, but gravity isn't the only thing that bends the flow of moments. Speed does too. The faster you move through space, the slower you move through time. This is velocity-time dilation, the consequence of Einstein's special theory of relativity, and it reveals something profound. Space and time are not separate. They're part of a single fabric, and how you move through one affects how you move through the other. Let's start with the foundation. In 1905, Einstein proposed something radical. The speed of light is constant for all observers, no matter how fast they're moving. This seems simple, but it has staggering consequences. If you're standing still and shine a flashlight, light leaves the bulb at about 186,282 miles per second. Now, imagine you're on a spacecraft moving at half the speed of light, and you shine a flashlight forward. Common sense says the light should move faster, your speed plus light's speed, but it doesn't. Light still travels at exactly 186,282 miles per second relative to you. The speed of light never changes. For this to be true, something else has to give, and what gives is time itself. When you move faster through space, your clock relative to someone who's stationary ticks more slowly. You age more slowly, time stretches. This isn't a trick of perception. It's a fundamental property of the universe. Motion through space and motion through time are inversely related. The faster you go, the slower time flows for you. Here's a concrete example that proves this happens. Deep in Earth's atmosphere, cosmic rays high-energy particles from space collide with air molecules and create exotic particles called muons. Muons are unstable. They decay into other particles in about 2.2 microseconds on average. That's their lifetime when they're at rest. Now, moons created high in the atmosphere are moving at about 98% the speed of light. At that speed, they should only travel about 2,000 feet before decaying not nearly enough to reach the ground. And yet muon detectors on Earth's surface register thousands of them every second. How do they survive the journey? Because from our perspective, their clocks are running slowly. At 98%, the speed of light time dilation stretches their 2.2 microseconds into about 16 microseconds, enough time to travel roughly 15,000 feet and reach the ground. The muons don't feel any different. From their perspective, they live for 2.2 microseconds just as always. But the distance to the ground is contracted in their frame of reference. It's shorter for them than for us. Both perspectives are correct. Time dilation and length contraction are two sides of the same coin, and together they explain why particles that should never reach us do. This is real, this is measured, this happens billions of times a day, and it's not limited to exotic particles. It applies to everything that moves, including us. Now, let's return to the twins. Imagine one twin stays on Earth while the other travels to Alpha Centauri, about 4.37 light-years away. The traveling twin boards a spacecraft capable of accelerating to 90% the speed of light. From Earth's perspective, the journey takes about 9.7 years out and 9.7 years back, roughly 19.4 years total. But for the traveling twin, time is moving more slowly. At 90%, the speed of light time dilation reduces their experience of the journey to about 8.5 years. When they return, the Earth twin has aged 19.4 years. The space twin has aged only 8.5 years. The difference is nearly 11 years. This is not a thought experiment anymore. We've tested this not with humans traveling near light speed, but with precise clocks and astronauts in orbit. Astronaut Scott Kelly spent 340 days aboard the International Space Station, orbiting at about 17,500 miles per hour. When he returned, scientists compared his biological markers to those of his identical twin brother, Mark Kelly, who stayed on Earth. Scott aged slightly less than Mark by about 8.6 milliseconds. It's a tiny fraction of a second, but it's real. Scott Kelly is measurably younger than his twin because he moved faster. Think about that. By moving at orbital speeds for less than a year, Scott Kelly shaved milliseconds off his aging. If he'd been moving at a significant fraction of light speed, the difference would be years, decades. This isn't science fiction. It's the reality of how space-time works. But here's where people often get confused. They ask, if motion is relative, why does the traveling twin age less? From the spaceship's perspective, isn't Earth moving away at high speed? Shouldn't the Earth twin age less? This is the paradox part of the twin paradox. Except it's not actually a paradox. The key is acceleration. The traveling twin has to accelerate to reach high speed, then decelerate to turn around, then accelerate back toward Earth, then decelerate to land. The Earth twin never accelerates. They remain in an inertial reference frame, a frame that's not accelerating. Acceleration breaks the symmetry. The twin who accelerates is the one who experiences less time. Relativity doesn't say all motion is equivalent. It says all constant motion is equivalent. Acceleration is absolute, and it's acceleration that determines who ages less. This has been confirmed not just with astronauts, but with atomic clocks flown in airplanes, the same Havuli-Keating experiment we discussed earlier. The eastward flying clock, moving with Earth's rotation, experienced more velocity and thus aged slightly less. The westward flying clock moving against Earth's rotation experienced less velocity and aged slightly more. Both results matched Einstein's predictions within experimental error. Velocity time dilation is not a hypothesis. It's a fact of nature. Now, let's scale this to the extremes. Particle accelerators like the Large Hadron Collider at CERN routinely accelerate protons to 99.9999991%, the speed of light. At this speed, time dilation is enormous. From our perspective, those protons live far longer than they would at rest by a factor of about 7,000. A particle that would normally decay in microseconds survives for milliseconds because its internal clock is barely ticking. Engineers designing the collider had to account for this. They had to calculate not just the paths particles would take through space, but the time dilation they would experience at relativistic speeds. Without Einstein's equations, the machine wouldn't work. Here's another stunning example. Cosmic rays particles from supernovae and other violent events sometimes strike Earth's atmosphere at even higher speeds, 99.999999999%, the speed of light or more. At these speeds, time dilation becomes extreme. A particle that should decay in nanoseconds might survive for seconds or longer from our perspective. These particles cross the entire atmosphere, which should be impossible given their short lifetimes. But time dilation makes it possible. The universe itself is constantly demonstrating relativity to us. So, what does this mean for human space travel? If we could build a spacecraft capable of reaching 99%, the speed of light, a journey to a star 50 light years away, would take about 50 years from Earth's perspective. But for the astronauts' onboard time, dilation would compress the experience. At 99%, light speed time slows down by a factor of about 7. The astronauts would experience the journey as roughly 7 years. They'd arrive biologically only 7 years older, while Earth would have aged 50 years. Everyone they knew would be older or gone. This is the cost of traveling close to light speed. You trade distance through space for distance through time. And if you pushed even closer to light speed, at 99.99%, the speed of light, the time dilation factor becomes about 71. A 100-year journey from Earth's perspective would feel like less than 1.5 years to the travelers. You could cross the galaxy in a human lifetime, your lifetime, even though thousands of years pass on Earth. You'd return to a world utterly transformed, where everyone you knew had died centuries ago. This is the strange gift of relativity. It allows you to travel vast distances, but only by leaping forward in time. Have you ever wondered what it would feel like to move that fast? The strange thing is, it wouldn't feel strange at all. Inside your spacecraft, time would seem normal. Your heartbeat, your breathing, the ticking of your clock, all perfectly regular. You wouldn't sense the time dilation. It's only when you compared your clock to Earth's, or when you returned and saw how much time had passed there, that the difference would reveal itself. This is what makes relativity so mind-bending. There's no universal clock. There's no correct time. Every observer, every object in motion carries their own time with them. Your time is just as real as mine, even if we've experienced different amounts of it. The universe doesn't care which one is right. Both are true simultaneously. Here's a common misconception. People think time dilation means time slows down in some absolute sense. It doesn't. From your own perspective, time always flows normally. You always experience 1 second per second. It's only when you compare your clock to someone else's, someone moving differently than you, that the difference appears. Time dilation is a relative effect, not an absolute one. It exists only in the relationship between observers. Another misconception. People think you have to be moving near light speed for time dilation to matter, but it happens at all speeds. Even walking across the room makes your clock tick infinitesimally slower than someone sitting still. The effect is tiny billionths of a nanosecond, but it's there. The equations don't have a minimum speed. They apply universally. It's just that at everyday speeds, the differences are so small that we never notice them. But once you reach orbital speeds or significant fractions of light speed, the effects become measurable and eventually dramatic. The twin paradox teaches us something fundamental. Motion through space-time is a journey with consequences. The path you take through the universe determines how much time you experience. Two people can start at the same event, the same point in space and time, and reunite at another event. But if they take different paths through space-time, they'll have aged differently. It's like two hikers starting at the base of a mountain and meeting at the summit. One takes a steep, direct path. The other takes a winding, gentle trail. They cover different distances and experience different exertions, even though they start and end at the same places. Space-time is similar, except what varies isn't just distance, it's time itself. This is the legacy of Einstein's special relativity. It dismantled the idea that time is universal and absolute. It revealed that time is personal, local, dependent on motion. And when combined with general relativity, where gravity also warps time, the picture becomes even richer. You're not just living in space, you're not just living in time. You're living in space-time, a dynamic landscape shaped by mass and motion, where every path you take, every speed you reach, changes how much time you experience. The traveling twin returns younger, not because of some trick, but because they've taken a different path through space-time, a path that trades space for time, distance for aging. And this exchange is built into the very fabric of reality. But gravity and speed together create even stranger effects. When you combine them, when you venture near objects so massive and so dense that space-time itself is torn into knots, time doesn't just slow, it nearly stops. And that's where our journey takes us next, into realms where clocks don't tick, where seconds stretch into eternities, where the universe reveals just how extreme time's flexibility can be. Right now in your pocket or on your wrist, you're carrying a device that wouldn't work without Einstein. Your phone knows exactly where you are down to a few feet because it's constantly communicating with satellites 12,500 miles above Earth. But here's what most people don't realize: those satellites are living in a different time stream than you are. Their clocks are ticking faster than yours. And if engineers hadn't accounted for this, if they hadn't built Einstein's equations directly into the system, GPS would fail within minutes. Your map would drift. Your navigation would collapse. All because time moves differently up there than down here. This is the hidden miracle of GPS. It's not just a positioning system. It's a relativistic time translation machine constantly correcting for the fact that time itself flows at different rates across the space between you and the satellites above. The global positioning system relies on a constellation of at least 24 satellites orbiting Earth. Each one carries an atomic clock, extremely precise timepieces that can measure billionths of a second. When you use GPS, your device receives signals from multiple satellites. Each signal includes a timestamp, the exact moment the satellite sent it. Your phone calculates how long each signal took to arrive by comparing the satellite's timestamp to its own clock. Since radio waves travel at the speed of light, the phone can determine the distance to each satellite. With distances to at least 4 satellites, it can triangulate your exact position on Earth. But here's the problem. This entire system depends on all the clocks yours and the satellites being perfectly synchronized. If the clocks are off by even a microsecond, the calculated distances are wrong. Light travels about 1,000 feet per microsecond. So, a 1 microsecond error in time translates to a 1,000-foot error in position. If the satellite clocks drifted just 38 microseconds per day, the actual amount they drift without relativistic corrections, your GPS would be off by more than 7 miles after a single day. Within a week, it would place you in the wrong state. The system would be worthless. So why do the satellite clocks drift? Because they're experiencing 2 types of time dilation simultaneously. And these 2 effects work in opposite directions. First, there's velocity time dilation. The satellites orbit at about 8,700 miles per hour. At this speed, special relativity predicts their clocks should tick more slowly than clocks on the ground, about 7 microseconds slower per day. This is the same effect we explored with the twin paradox motion through space, slows motion through time. Second, there's gravitational time dilation. The satellites orbit at high altitude where Earth's gravity is weaker. General relativity predicts their clocks should tick faster than clocks on the ground, about 45 microseconds faster per day. Gravity's grip is looser up there, so time flows more freely. Now comes the remarkable part. These two effects don't cancel out. Velocity slows the clocks by 7 microseconds per day. Gravity speeds them up by 45 microseconds per day. The net result is that satellite clocks run 38 microseconds fast every day, 0.0000038 seconds. That might sound negligible, but remember, GPS measures time in nanoseconds. A 38 microsecond error is massive. Light travels more than 7 miles in that time. Without correction, GPS accuracy would degrade catastrophically. So, how do engineers solve this? They don't try to stop the time dilation. They can't. Time dilation is a fundamental property of space-time, not a malfunction. Instead, they pre-adjust the satellite clocks before launch. Atomic clocks on Earth are designed to tick at exactly 9,192,631,770 oscillations per second. That's the definition of a second based on the cesium-133 atom. But the clocks installed in GPS satellites are deliberately programmed to tick at a different rate, 10,229,999,995.43 oscillations per second, which is slightly slower. Once the satellites reach orbit and experience the combined effects of velocity and gravitational time dilation, their slower tick rate compensates perfectly. From our perspective on the ground, they appear to tick at the correct rate. The clocks are wrong on purpose so they can be right in context. Think about what this means. Every time you check your location on your phone, you're relying on a correction that wouldn't exist without Einstein's theories. GPS is applied relativity. It's a technology that couldn't work in a Newtonian universe where time is absolute. The fact that your phone can guide you to an address you've never visited, that autonomous cars can navigate streets that airplanes can land safely in fog, all of this depends on accounting for time dilation. Without Einstein, none of it functions. Let's break down the numbers more carefully to understand why this matters so much. GPS satellites orbit at an altitude of about 12,550 miles above Earth's surface. At this height, they're far enough from Earth's center of mass that gravity's effect on time is noticeably reduced compared to the surface. The formula from general relativity tells us that a clock in a weaker gravitational field ticks faster. The calculation shows that at GPS orbital altitude, this gravitational time dilation causes clocks to gain about 45.9 microseconds per day compared to a clock on Earth's surface. At the same time, those satellites are moving at roughly 8,700 miles per hour relative to an observer on the ground. Special relativity tells us that a moving clock ticks more slowly than a stationary one. The calculation for this velocity time dilation shows the clocks lose about 7.1 microseconds per day. When you subtract the velocity effect from the gravitational effect, you get a net gain of about 38.8 microseconds per day. This is the combined relativistic correction that must be applied. Now here's where it gets even more interesting. The corrections aren't uniform for all satellites or all locations. GPS satellites don't follow perfectly circular orbits, they're slightly elliptical. This means their altitude varies, and so does their speed. When a satellite is at the lowest point in its orbit, it's moving faster and experiencing slightly stronger gravity. Both effects change the time dilation. Engineers must continuously calculate these variations and adjust accordingly. The GPS system doesn't just apply a single static correction. It dynamically accounts for each satellite's changing position and velocity in real time. And it's not just the satellites that need correction. Your phone's clock down here on Earth's surface is also subject to gravitational time dilation. But this effect varies depending on your altitude. If you're standing at sea level, you're deeper in Earth's gravitational well than someone standing on a mountain. Your clock ticks slightly slower. GPS receivers in airplanes flying at 30,000 feet experience weaker gravity than receivers on the ground. Their clocks tick faster. High-precision GPS systems used in surveying and scientific research must account for this too. They need to know not just your horizontal position, but your altitude, because altitude affects the flow of time and thus the accuracy of the timing signals. Consider what happens if you ignore these effects. In 2000, researchers ran a simulation to see how quickly GPS would fail without relativistic corrections. The results were stark. After just 2 minutes, the positioning error would be about 1 mile. After an hour, it would be about 30 miles. After a day, the system would be reporting locations more than 200 miles away from the true position. The satellites would still be broadcasting signals, and your phone would still be receiving them. But the math would be wrong because the clocks wouldn't agree on what time it is. The entire system would collapse into chaos. This isn't a theoretical concern. When GPS was first being developed in the 1970s, some engineers were skeptical that relativistic effects would matter. They argued that the corrections were too small to worry about, that Newtonian physics would be sufficient. But others insisted on running the calculations, and those calculations showed unmistakably that relativity couldn't be ignored. Initial tests confirmed it. Without the corrections, the system failed. Today, every GPS satellite launched, every GPS receiver manufactured, has Einstein's equations embedded in its firmware. Relativity isn't optional, it's essential. Here's a common misconception people have. They think GPS corrects for time dilation by constantly synchronizing the satellite clocks with ground clocks. That's not quite how it works. The pre-launch adjustment to the satellite clock frequency is the primary correction. Once in orbit, the satellite's clocks run at what appears to be the correct rate from our perspective. However, ground control stations do monitor the satellites continuously and make small adjustments as needed. Not because time dilation is changing, but because atomic clocks, even the best ones, can drift slightly over time due to other factors like temperature fluctuations or aging components. The relativistic correction is baked into the design. The ongoing adjustments are fine-tuning. Another thing people get wrong, they think time dilation only matters for GPS because the satellites are so far away. Distance alone doesn't cause time dilation. Altitude matters because it changes your position in Earth's gravitational field, which affects gravitational time dilation. And velocity matters because it affects velocity time dilation. Two satellites at the same altitude but different speeds would experience different amounts of time dilation. It's not about how far away something is, it's about how it's moving and where it is in the gravitational landscape. Now let's think about what this means for other technologies. GPS isn't the only system that depends on precise timekeeping. The internet, for example, relies on synchronized clocks to route data packets, coordinate transactions, and timestamp communications. Financial markets use atomic clocks to timestamp trades to within microseconds, ensuring fairness and preventing fraud. Telecommunications networks synchronize signals across vast distances. All of these systems assume that time is consistent, but it's not. Time varies with altitude and velocity. As our technologies become more precise, we'll need to account for relativistic effects in more and more applications. Consider the stock market. High-frequency trading firms compete to execute trades in millionths of a second. They place their servers as close as possible to stock exchange data centers to minimize signal delay. But even at these scales, relativistic effects could become relevant. A clock on the ground floor of a building ticks slightly slower than a clock on the top floor, Because of the difference in gravitational potential, it's tiny but measurable. As trading speeds increase, firms may eventually need to account for this. Time dilation could become a competitive advantage. Or think about future space missions. When humans establish a permanent base on the moon, we'll need a lunar GPS system. But the moon's gravity is weaker than Earth's, and its lack of atmosphere means satellites can orbit much lower. Time dilation on the moon will be different. Engineers are already planning for this, designing what's called the Lunar Time Standard, a framework for keeping time on the moon that accounts for its unique gravitational environment. It's not enough to just move our clocks there. We need to understand how time flows differently on another world and build systems that can translate between reference frames. And what about Mars? Mars missions already deal with signal delays. It takes light between 4 and 24 minutes to travel between Earth and Mars, depending on the planet's positions. But there's also time dilation. Mars has lower gravity than Earth, so time on Mars runs slightly faster. For robotic missions, this barely matters. But when humans live on Mars for months or years, the cumulative difference will add up. Timekeeping systems will need to account for this, not just for navigation, but for coordinating activities between the two planets. Do you realize how remarkable this is? The device in your pocket is performing relativistic calculations, thousands of times per second, translating between different time streams, compensating for effects that Einstein predicted over a century ago. You ask it for directions, and it silently navigates the curved geometry of space-time to give you an answer. GPS is proof, everyday ubiquitous proof, that time is not absolute, that the universe operates according to principles that would have seemed like magic to our ancestors. And here's the beautiful irony: most people use GPS without ever thinking about relativity. They trust that the system works, that the blue dot on their screen accurately represents their location. And it does work because engineers took Einstein seriously, because they didn't dismiss relativistic effects as too small to matter, because they built time dilation corrections into the very foundation of the technology. GPS is a triumph not just of engineering, but of theoretical physics applied to practical problems. This is what makes science so powerful. It reveals truths about the universe that seem absurd, time flowing at different rates, clocks disagreeing about what now means, and then uses those truths to build tools that change civilization. GPS has revolutionized navigation, transportation, agriculture, disaster response, and countless other fields. And none of it would be possible if we lived in a universe where time was absolute. So, the next time you glance at your phone to see where you are, remember you're not just using a positioning system. You're experiencing Einstein's legacy in real time, navigating a world where time bends and stretches, where clocks tick at different rates, depending on where they are and how they're moving. You're living proof that relativity isn't just abstract mathematics scribbled on a chalkboard. It's the hidden architecture of modern life. But as precise as GPS is, as miraculous as it seems to correct, for microseconds of time dilation, it's nothing compared to what happens near the most extreme objects in the universe. There are places where time doesn't just slow slightly, it nearly stops, where the very concept of now breaks down. And those places hold secrets about the ultimate limits of reality itself. Imagine watching a clock fall toward a black hole. At first, it ticks normally, second by second, just as any clock would. But as it gets closer to the edge, something strange begins to happen. The ticking slows. The hands move more and more sluggishly. The seconds stretch into minutes, then hours, then years. And finally, as the clock reaches the point of no return, the event horizon, it stops completely. Not because it's broken, not because it's run out of power, but because time itself at that boundary has stretched to infinity. From your safe distance, that clock will remain frozen forever, suspended at the threshold of the black hole, never quite crossing over. This is gravitational time dilation, taken to its most extreme limit, a place where time doesn't just slow down. It nearly stops. Black holes are the universe's ultimate demonstration of how profoundly gravity warps time. And understanding what happens to time near them reveals some of the most mind-bending truths about reality. Let's start with what a black hole actually is. When a massive star, at least 20 or 30 times the mass of our sun, exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses catastrophically, and if there's enough mass, nothing can stop it. The collapse continues until all that mass is compressed into an infinitely small point called a singularity. Around this singularity lies the event horizon, an invisible boundary where the escape velocity equals the speed of light. Once anything crosses the event horizon, not even light can escape. That's why we call them black holes. They don't emit light, they trap it. But here's what most people don't fully grasp. The event horizon isn't a physical surface. It's not a wall or a membrane. It's a boundary in space-time itself, a point of no return, defined purely by gravity's overwhelming strength. And at this boundary time, dilation becomes infinite. Clocks approaching the event horizon, as seen by a distant observer, slow down asymptotically approaching zero speed, but never quite stopping. They get closer and closer to freezing, but mathematically they never completely freeze. They just take infinite time to cross. This creates one of the strangest paradoxes in physics. Imagine an astronaut falling into a black hole. From the astronaut's perspective, from their own reference frame, everything seems normal. They pass through the event horizon in finite time. They don't feel anything special at the moment of crossing. If the black hole is large enough, the tidal forces might not even be strong enough to tear them apart yet. They continue falling inward toward the singularity. But from your perspective, watching from a safe distance far away, the astronaut never crosses the horizon. You see them slow down as they approach. Their movements become sluggish. Light from them becomes redder and dimmer as it struggles to escape the intense gravity. Eventually, they fade from view, frozen in time just outside the event horizon. According to your clock, they never cross. According to their clock, they do. Both perspectives are correct. This is relativity at its most extreme. Let's put some numbers to this. Consider Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy. It has a mass of about 4 million times that of our Sun. Its event horizon, called the Schwarzschild radius, is roughly 12 million miles across about 17 times the diameter of the Sun. If you were orbiting just outside the event horizon of Sagittarius, a star-time dilation would be enormous. For every hour that passed for you, several hours, or even days, depending on how close you are, would pass for someone far from the black hole. Your clock would tick, your heart would beat. Your thoughts would flow at what feels like a normal rate to you. But the universe outside would be aging faster. Now, imagine getting even closer, hovering just a few miles above the event horizon. Time dilation intensifies. For every second you experience, minutes pass in the outside universe. If you could hover there for what feels like 1 hour to you, decades might pass outside. Your entire lifetime near the event horizon could correspond to thousands or millions of years in the universe beyond. You'd become unstuck from time, living in a slower stream, while the cosmos rushes forward without you. This isn't science fiction. This is what Einstein's equations predict, and we've observed evidence of it. In 2020, astronomers watched a star called S2 make a close approach to Sagittarius, A star. As S2 swung around the black hole at about 2.5%, the speed of light they measured a redshift in the star's light, a stretching of wavelengths caused by gravitational time dilation. The star's light was climbing out of a deep gravitational well, and in doing so, it lost energy. Its wavelength stretched, shifting toward the red end of the spectrum. This redshift matched Einstein's predictions almost perfectly. We were watching time dilation in action, written in the light of a star dancing around a black hole. But black holes aren't the only objects that create extreme time dilation. Neutron stars, the collapsed cores of stars that weren't quite massive enough to become black holes, also warp space-time dramatically. A neutron star packs about 1.4 times the sun's mass into a sphere only about 12 miles across. That's roughly the size of a city, but with more mass than the sun. The density is incomprehensible. A sugar cube-sized chunk of neutron star material would weigh about 1 billion tons on Earth. Gravity on the surface of a neutron star is about 200 billion times stronger than Earth's. At that gravity time, dilation is significant. If you could stand on a neutron star's surface, though, you'd be instantly crushed. Time would pass about 30% slower for you than for someone far away in space. This has been confirmed through observations. Neutron stars often emit regular pulses of radiation as they spin, acting like cosmic lighthouses. Astronomers measure these pulses with extraordinary precision. When they account for the time dilation caused by the neutron star's gravity, the timing matches Einstein's predictions. The pulses are stretched in time, arriving slightly later than they would if space-time were flat. Now, let's talk about the scene in the movie Interstellar that captured everyone's imagination, Miller's Planet. In the film, the crew lands on a planet orbiting a supermassive black hole named Gargantua. Due to extreme gravitational time dilation, 1 hour on the planet's surface equals 7 years back on Earth. When the crew returns to their ship, after what felt like a few hours, decades have passed for the crew member who stayed behind. He's aged. They haven't. Is this scientifically plausible? The answer is yes, mostly. The math works out if the planet is orbiting very close to the black hole's event horizon, skimming along the edge of the point of no return. At that distance, gravitational time dilation would indeed be extreme enough to create such a dramatic difference. However, there's a catch. Orbiting that close to a black hole would subject the planet to enormous tidal forces. The difference in gravitational pull between the near side and far side of the planet would likely tear it apart. The planet would also need to be orbiting at nearly the speed of light to avoid falling in, which introduces its own problems. So, while the time dilation depicted in the film is theoretically possible, the scenario requires some very specific and somewhat unlikely conditions. But as a demonstration of how extreme time dilation can get near a black hole, it's remarkably accurate. Here's what many people misunderstand about black holes. They think of them as cosmic vacuum cleaners, sucking everything in. But black holes don't suck any more than any other massive object. If you replace the sun with a black hole of equal mass, Earth's orbit wouldn't change. We'd keep orbiting at the same distance, the same speed. We'd freeze and die from lack of sunlight, but we wouldn't get pulled in. The difference is that black holes compress mass into such a small volume that you can get much closer to their center of mass before encountering a surface. And the closer you get, the more intense the gravitational field, the more extreme the time dilation. Another common misconception: people think that once you cross the event horizon, you're instantly crushed or destroyed. That's not necessarily true, at least not for supermassive black holes. The tidal forces at the event horizon of a supermassive black hole, like Sagittarius A star, are actually quite mild. You could cross the horizon and for a brief time continue to exist relatively intact. It's only as you fall deeper, approaching the singularity at the center, that tidal forces become lethal. For smaller black holes, stellar mass black holes created from individual stars, the tidal forces at the event horizon are much stronger, and you'd likely be torn apart before crossing. This stretching effect is called spaghettification, and it's a real term in astrophysics. Your feet being closer to the singularity than your head would experience stronger gravity and be pulled away from your head. You'd be stretched into a long, thin strand. But let's return to the question of time. Why does time slow down near a black hole? It goes back to the curvature of space-time. Mass tells space-time how to curve, and space-time tells mass how to move. Near a black hole, space-time is curved so steeply that the downward slope, the pull toward the singularity, becomes nearly vertical. Time, which is one dimension of space-time, is also stretched by this curvature. The more curved space-time is, the more time is dilated. Think of it this way: when you're far from any massive object, space-time is relatively flat. Time flows at its maximum rate. As you approach a massive object, space-time curves. Time begins to flow more slowly. Near a black hole, space-time curves so intensely that time's flow slows to a crawl. At the event horizon, the curvature is so extreme that time from an outside perspective essentially stops. The event horizon is the edge of a region where space-time has been bent so far that all paths lead inward. Even paths through time lead inward. There is no future that exists outside the black hole once you've crossed. Your future is inside toward the singularity. This leads to a profound realization. Black holes are not just objects in space. They're objects in time. They're regions where the normal flow of time breaks down, where the past and future become scrambled, where the concept of now loses meaning. When you approach a black hole, you're not just moving through space, you're moving through a part of the universe where time itself is collapsing. And here's something even stranger. Stephen Hawking showed that black holes aren't perfectly black. They emit a faint radiation now called Hawking radiation. Due to quantum effects near the event horizon, this radiation causes black holes to slowly evaporate over unimaginably long time scales. A black hole with the mass of the sun would take about 10 to the power of 67 years to evaporate. But from the perspective of someone falling into the black hole, this evaporation happens almost instantly. Because time dilation is so extreme near the event horizon, processes that take eons from an outside perspective unfold rapidly from the inside. This creates a paradox. From outside, black holes last nearly forever. From inside, they might vanish in a flash. What does it feel like to approach a black hole? Imagine you're in a spacecraft falling inward. You look back at the universe you're leaving behind. Because of time dilation and the bending of light, you see something extraordinary. The universe behind you appears to speed up. Stars move across the sky in fast forward. Galaxies rotate visibly. The cosmos ages before your eyes. Light from the distant future streams toward you, compressed by the warped space-time. In your final moments before crossing the event horizon, you might witness the end of stars, the death of galaxies, perhaps even the far future of the universe itself, all compressed into a few subjective seconds. It's like falling forward in time, watching the universe age while you remain young. Do you ever wonder what it would be like to witness eternity near a black hole you almost can? Time becomes a landscape, not a river. And the most extreme object in that landscape is the black hole itself, a well so deep that time itself cannot climb out. This is the power and the terror of black holes. They don't just trap matter and light, they trap time. They're prisons not just in space, but in the fourth dimension. And they show us that time is not an immutable constant. It's a flexible, stretchable, breakable thing, something that can slow, stop, and perhaps even reverse under the right conditions. But black holes aren't the only places in the universe where time behaves strangely. There are other worlds, other objects, other corners of the cosmos, where the flow of moments diverges from our own, where clocks tick at different rhythms, and where the question, "What time is it?" has no single answer. Imagine visiting every planet in our solar system, carrying a perfect clock with you. You synchronize it with Earth's time before you leave. First stop Mercury, where you land on the scorching surface and set your clock down. Next Venus, then Mars, then the moons of Jupiter and Saturn. Finally, you journey to the edge of the solar system, to distant Neptune and beyond. When you return to Earth and compare all these clocks, you discover something astonishing. They no longer agree. Each clock has ticked at a slightly different rate, shaped by the unique gravitational field of the world where it sat. Time itself flows differently on every celestial body in the cosmos. There is no universal now. There are only local nows, each one unique to its place in the fabric of space-time. This is the reality of our universe. Time is not uniform. Every world, every moon, every asteroid experiences its own temporal rhythm and understanding. These differences is becoming crucial as humanity prepares to become a multi-planetary species. Let's start close to home, our moon. The moon orbits Earth at an average distance of about 238,855 miles. At this distance, it's significantly farther from Earth's center of mass than we are on the surface. Earth's gravitational pull is weaker there, which means time on the moon runs faster than time on Earth. How much faster? Calculations show that a clock on the moon gains about 56.02 microseconds every day compared to a clock on Earth's surface. Over the course of a year, that's about 20 milliseconds. It sounds trivial, and for short, Apollo missions in the 1960s and 70s it was. The astronauts spent only a few days on the lunar surface, so the time difference was negligible. But now, as we plan permanent lunar bases and regular traffic between Earth and the Moon, this difference matters enormously. NASA and the European Space Agency are currently developing what they call a lunar time standard, a unified timekeeping system for the Moon. Why is this necessary? Because future lunar operations will require precision. Spacecraft will need to navigate between Earth and the Moon. Communication systems will need to synchronize signals. Scientific experiments will need accurate timestamps. If Earth clocks and Moon clocks drift apart by milliseconds per year, over time, these small differences compound into errors that can throw off navigation, corrupt data, and create dangerous mismatches in timing critical operations. The Lunar Time Standard will define a reference frame for time on the Moon, just as we have time zones and standards here on Earth. It's not science fiction, it's practical infrastructure for the future of space exploration. But the Moon is just the beginning. Consider Mars the next frontier for human exploration. Mars is less massive than Earth, only about 11% of Earth's mass, and it has a weaker gravitational field. A clock on the Martian surface ticks faster than a clock on Earth's surface by about 0.3 milliseconds per day. That might seem tiny, but over the course of a 2-year Mars mission, the typical length for a round trip, including surface time, the difference adds up to about 200 milliseconds. For robotic missions that are mostly autonomous, this is manageable. But when humans are living on Mars, coordinating activities with mission control on Earth, the time difference becomes significant. Engineers will need to build Martian timekeeping systems that account for this faster flow of time. And it's not just about keeping schedules, it's about physics. Chemical reactions, radioactive decay, biological processes, all of these unfold at rates determined by the local flow of time. An experiment conducted on Mars will run slightly faster in an absolute sense than the same experiment on Earth. If scientists are comparing data from both planets, they need to account for this difference. Time dilation isn't just an abstract curiosity. It's a correction factor that must be applied to real measurements. Now, let's venture farther out. Jupiter, the largest planet in our solar system, has a mass about 318 times that of Earth. Its gravitational field is correspondingly stronger. On Jupiter's surface, though Jupiter is a gas giant with no solid surface, gravity is about 2.5 times stronger than Earth's. This means time runs slower there than on Earth. A clock on Jupiter would lose time compared to an Earth clock ticking more slowly in the deeper gravitational well. We haven't sent precision clocks to Jupiter to measure this directly, but the effect is predicted by Einstein's equations and has been confirmed in countless other contexts. Jupiter's moons experience different time flows as well, depending on their distance from the planet. Io, the innermost large moon, sits deep in Jupiter's gravitational well and experiences stronger time dilation than distant Callisto. The moons of Saturn present another fascinating case. Titan, Saturn's largest moon, is a world of thick atmosphere and liquid methane lakes. It's about 759,000 miles from Saturn's center. Time on Titan runs faster than on a hypothetical position at Saturn's cloud tops, because Titan is farther from Saturn's mass. But compared to Earth, Titan's time flow is different again, shaped by both Saturn's gravity and the Sun's gravity at that distance. Future missions to Titan, potentially including landers and even submarines to explore its lakes, will need to account for these relativistic effects in their navigation and communication systems. Here's where it gets even more interesting. Not all time dilation comes from gravity. Remember, velocity also affects time. The planets orbit the sun at different speeds. Mercury, closest to the sun, zips along at about 29 miles per second. Neptune, at the edge of the solar system, crawls at about 3.4 miles per second. These different orbital velocities create velocity-time dilation. A clock on Mercury experiences both the gravitational time dilation from being deep in the sun's gravitational well and velocity-time dilation from its fast orbital motion. The two effects work in opposite directions. Gravity slows the clock, velocity slows it further, and the combination determines the net time flow. Calculations show that on Mercury's surface, time runs about 0.0219 seconds, slower per year than it would in deep space far from the sun. That's primarily due to the sun's gravitational influence. Mercury orbits so close to the sun, only about 36 million miles on average, that it sits in a steep part of the sun's gravitational well. Time there is measurably stretched. In fact, this time, dilation affects Mercury's orbit itself. Mercury's elliptical orbit precesses the point of closest approach to the sun, slowly rotates over time. Newtonian physics predicts most of this precession, but there's a small discrepancy. Einstein's general relativity, which accounts for time dilation and space-time curvature, predicts the remaining 43 arcseconds per century of precession that Newton's laws can't explain. Observations match Einstein's prediction exactly. This was one of the first confirmations of general relativity, and it's a direct consequence of time flowing differently near the sun. Now consider spacecraft traveling between worlds. The Parker Solar Probe, launched in 2018, is designed to study the sun's corona. It swoops to within about 4 million miles of the sun's surface, closer than any previous spacecraft. At that distance, traveling at speeds exceeding 430,000 miles per hour, the probe experiences extreme time dilation from both gravity and velocity. Calculations suggest that the onboard clock over the course of the mission will lose a few microseconds compared to clocks on Earth. Mission planners account for this in the probe's data timestamps and navigation. Every measurement the probe takes is tagged with a time, and that time must be corrected for relativistic effects to be accurate. This isn't just theoretical. The Juno spacecraft orbiting Jupiter, the Cassini mission that orbited Saturn, and even the Voyager probes now in interstellar space all experience time slightly differently than we do on Earth. When Voyager 1, now more than 15 billion miles from the sun, sends back a signal, we receive data, time-stamped by its onboard clock. That clock has been ticking in a region of weaker gravity than Earth's, and it's been moving at high velocity for over 40 years. The cumulative time difference is small fractions of a second, but it exists. Engineers incorporate these corrections into their tracking models. Here's a question worth pondering. If every world in the universe has its own time flow, how do we even define simultaneous events? If something happens on Mars at the same time as something on Earth, what does that mean? The truth is, simultaneity is relative. Events that appear simultaneous in one reference frame may not be simultaneous in another. This is a fundamental insight of relativity. There is no absolute simultaneity. There's only simultaneity within a given reference frame. For practical purposes, when coordinating activities across different worlds, we'll define simultaneity using agreed-upon reference frames, likely something like a solar system Barai-centric coordinate time, which defines time relative to the center of mass of the entire solar system. But this is a convention, not an absolute truth. Let's talk about white dwarfs again, because they're some of the most extreme accessible examples of gravitational time dilation, outside of neutron stars and black holes. White dwarfs are the remnants of stars like our sun. After they exhaust their fuel, they shed their outer layers and leave behind a dense core, typically about the size of Earth, but with half the sun's mass. Gravity on a white dwarf's surface is about 100,000 times stronger than on Earth. Time dilation there is significant. A clock on a white dwarf would tick about 0.01% slower than a clock far from any gravitational influence. That means, for every billion seconds that pass far from the white dwarf, the clock on its surface only ticks about 999.9 million seconds. Over a year, that's a difference of roughly 3,000 seconds, about 50 minutes. If you could somehow survive on a white dwarf for a decade, you'd age about 8 hours less than someone far from any star. Astronomers have confirmed this time dilation by observing light from white dwarfs. The light emitted from the surface has to climb out of a deep gravitational well to reach us. In doing so, it loses energy, and its wavelength stretches a phenomenon called gravitational redshift. We measure this redshift in the spectra of white dwarfs, and it matches Einstein's predictions. The atoms on the white dwarf's surface are vibrating at slightly lower frequencies because time there is flowing more slowly. When we observe them, we're literally seeing time dilation encoded in the light. Now, think about the implications for future exploration. When humans establish colonies on different worlds, Mars, the moons of Jupiter, each colony will be living in a slightly different time stream. A child born on the moon will age slightly faster than a child born on Earth. Over a 70-year lifespan, the difference is only about a second, but it's real. Martian colonists will age even faster relative to Earth. If we establish a base on Callisto, one of Jupiter's outer moons, residents there will experience time flowing at yet another rate. The human species will become temporally fragmented, each population ticking along at its own rhythm. This raises practical questions. If you're born on Mars, spend 20 years there, then return to Earth. How do you celebrate your birthday? Do you count Martian years or Earth years? Do you account for the time dilation difference? These questions sound trivial, but they highlight a deeper truth. As we spread across the solar system, we'll need new frameworks for understanding identity, age, and time itself. The concept of a single shared timeline for all of humanity will become obsolete. And there's a poetic dimension to this as well. Every world in the cosmos has its own song, its own tempo. Earth beats at one rhythm, the moon beats slightly faster, Mars faster still. Jupiter's moons beat to Jupiter's deep, slow drum. And black holes beat so slowly they might as well be frozen. We're learning that the universe is not a monolithic clock ticking uniformly everywhere. It's a symphony of clocks, each one keeping time at its own pace, and all of them valid, all of them true within their own reference frames. Have you ever stopped to imagine what it would feel like to live on a world where time flows faster or slower than here? You wouldn't feel any difference. Your heartbeat would seem normal. Your thoughts would flow at their usual pace. It's only when you compared your experience to someone elsewhere, someone in a different gravitational field, a different velocity, that the divergence would appear. Time is deeply, profoundly local. This is one of the most beautiful and humbling lessons of relativity. We tend to think of time as a universal backdrop, a stage on which the universe performs. But time is part of the performance. It's shaped by mass, warped by motion, and unique to every path through space-time. As we venture into the cosmos, we're not just exploring space, we're exploring time. We're discovering all the different ways moments can unfold, all the different rhythms the universe can beat. And this brings us to a crucial question. If time flows differently everywhere, what does that mean for the people who travel between these worlds? What happens to astronauts who spend months or years in space moving through different gravitational fields, traveling at high velocities? How much younger or older do they become compared to those who stay behind? The answers are both fascinating and measurable, and they're already affecting real people in orbit above us right now. On March 27, 2015, astronaut Scott Kelly launched to the International Space Station for a year-long mission. Back on Earth, his identical twin brother, Mark, also an astronaut, stayed behind. For 340 days, Scott orbited Earth at 17,500 miles per hour, while Mark remained on the ground. When Scott returned on March 1st, 2016, something remarkable had happened. Scott Kelly had aged less than his twin brother. Not by much, only about 8.6 milliseconds less, but measurably, undeniably less. The twin who traveled through space came back younger. This wasn't a thought experiment. This was real life, and it proved that time dilation isn't just something that happens to clocks and particles. It happens to people. This is the aging astronaut effect, the reality that space travel makes you younger, that every moment spent in orbit or journeying to another world is a moment stolen from the relentless march of time. And as humanity prepares for longer missions to the moon, to Mars, and perhaps beyond, this effect will become more pronounced, more significant, and more deeply woven into the experience of being human in space. Scott Kelly's mission was part of NASA's twin study designed to investigate how long-duration spaceflight affects the human body. Scientists compared every measurable aspect of Scott's biology, his genes, his cells, his cognition to Mark's. They wanted to understand the impact of microgravity radiation, isolation, and stress. But embedded within that study was also a test of relativity. Scott was moving fast relative to Earth, and he was farther from Earth's gravitational center. Both effects influenced how time flowed for him. The velocity-time dilation from his orbital speed slowed his clock slightly. The gravitational time dilation from being at higher altitudes sped it up slightly. When you combine the two effects, the velocity effect dominates, and the net result is that Scott's biological clock ticked slightly slower than Mark's. He experienced fewer moments. He aged less. 8 milliseconds over nearly a year doesn't sound like much, and in human terms, it isn't. But it's proof of principle. It demonstrates that the equations Einstein wrote over a century ago apply not just to atomic clocks and subatomic particles, but to living, breathing human beings. Your time, your biological processes, your heartbeat, your cells dividing, is subject to the same relativistic effects as everything else in the universe. You are not exempt from the curvature of space-time. Now, let's scale this up. The International Space Station orbits at about 250 miles above Earth, traveling at roughly 17,500 miles per hour. Astronauts who spend 6 months there age about 0.007 seconds less than they would have on Earth. That's 7 milliseconds, barely perceptible. But what if we go farther, faster, longer? What happens to astronauts on multi-year missions to Mars, or those who might one day journey to the outer solar system, or even to other stars? Consider a Mars mission. The journey to Mars takes about 7 to 9 months each way, depending on the alignment of the planets. A typical mission profile involves spending several months on the Martian surface before the return window opens. Total mission time, about 2 to 3 years. During the journey, the spacecraft travels at high velocity, around 24,000 miles per hour, for much of the transit. This velocity creates time dilation. Additionally, once on Mars, astronauts experience weaker gravity than on Earth, which means time on Mars flows slightly faster. When you calculate the combined effects of the journey and the surface stay, astronauts returning from a Mars mission will have aged slightly less than people who stayed on Earth by about 3 seconds over the course of a 3-year mission. It's still tiny, but it's measurable with modern atomic clocks. The real differences emerge when we consider missions to the outer solar system or beyond. Imagine a mission to Europa, one of Jupiter's moons located about 390 million miles from Earth. With current propulsion technology, such a journey could take 5 to 6 years one way. At the velocities required, astronauts would accumulate a time dilation effect of several milliseconds per year. Over a decade-long round trip, they might age about 0.1 seconds less than their Earthbound peers. Still small, but growing. And if we develop faster propulsion systems, nuclear rockets, ion drives, or even fusion engines that can reach significant fractions of the speed of light, the effects become dramatic. Let's imagine a more ambitious scenario. Suppose we develop a spacecraft capable of reaching 10% the speed of light, about 18,600 miles per second. At this speed, A journey to the nearest star system, Alpha Centauri, about 4.37 light-years away, would take roughly 44 years from Earth's perspective. But for the astronauts on board, time dilation kicks in. At 10% light speed, the time dilation factor is about 1.0. 0.5, meaning time passes about 0.5% slower for the travelers. Over 44 years, that's about 0.2 years, or roughly 2.6 months. The astronauts would experience the journey as 43.78 years instead of 44. They'd arrive at Alpha Centauri having aged about 2.5 months less than people on Earth. Now, push the speed higher. At 50%, the speed of light, the time dilation factor increases to about 1.155. A 44-year journey from Earth's perspective becomes about 38 years, for the travelers 6 years less. At 90%, the speed of light, the factor jumps to 2.29. The journey shrinks to about 19 years for the astronauts, while 44 years pass on Earth. They arrive having aged 25 years less than their peers back home. They step off the ship middle-aged while their childhood friends have grown old or died. This is the cost and the gift of traveling at relativistic speeds. Here's what many people get wrong about this. They think time dilation means the astronauts experience some kind of slow-motion existence, that they're thought sluggish and their heartbeats prolonged. That's not what happens. From the astronauts' perspective, time flows completely normally. They think breathe age at what feels like the regular pace. A year on board feels like a year. It's only when they compare their clocks to Earth's, or when they return and see how much time has passed there, that the difference reveals itself. Time dilation is a comparative effect, not a subjective one. Another misconception: people assume that because astronauts age less, they're somehow healthier or preserved by space travel. The biological effects of spaceflight radiation, exposure, muscle atrophy, bone density loss, can be quite harmful, and these outweigh any advantage from aging a few milliseconds slower. Scott Kelly, despite being technically younger than his twin, due to time dilation, experienced significant physical stress from his year in space. His telomeres, the protective caps on chromosomes, initially lengthened in space, which was unexpected, but they shortened again upon return to Earth. His gene expression changed. His body adapted to microgravity in ways that weren't all positive. Time dilation made him younger by milliseconds, but spaceflight made him biologically older in other measurable ways. The two effects don't cancel out. They're measuring different things. Now, let's talk about what this means for future long-duration missions. NASA is planning to return humans to the moon, with the Artemis program establishing a sustained presence there. The moon's surface has weaker gravity than Earth, so time runs faster there. Astronauts spending months or years on the moon will age slightly more by about 0.02 milliseconds per day compared to staying on Earth. Over a decade of lunar habitation, that's about 73 milliseconds. It's a small number, but it accumulates. More importantly, it's a measurable divergence in aging between populations. Moon-based humans and Earth-based humans will be living in different temporal streams. Mars colonization introduces even more complexity. Mars has about 38% of Earth's surface gravity. Time on Mars runs faster than on Earth, by about 0.3 milliseconds per day. A colonist who spends 20 years on Mars will have aged about 2 seconds more than if they'd stayed on Earth. But the journey to Mars involves high-velocity travel, which makes them younger. So, the total effect depends on how much time they spend traveling versus how much time they spend on the Martian surface. For someone who travels to Mars once and stays there permanently, the time dilation from the journey makes them younger by a fraction of a second. But decades on, Mars make them older by a few seconds. The surface time dominates. Now, imagine a future where humans are regularly traveling between Earth, the Moon, Mars, and stations in orbit. Spaceflight becomes routine. Some people spend most of their lives in space accumulating time dilation effects over decades. Others remain on Earth. Over a lifetime, the differences might amount to several seconds or even tens of seconds. It's not life-altering on an individual level, but it's philosophically profound. Identical twins born on the same day, one living on Earth and the other living in space, would age at slightly different rates. By age 80, they might differ in biological age by 10 or 20 seconds. Their clocks and their cells would tell different stories. Here's a real example from history that illustrates how even small time differences can add up. Sergei Krikalev, a Russian cosmonaut, holds the record for the most cumulative time in space, 803 days, over multiple missions. During those 803 days, he orbited Earth at high speed. Calculations show that Krikalev aged about 0.02 seconds less than he would have if he'd stayed on Earth, 20 milliseconds. It's the largest time dilation effect any human has ever experienced. Krikalev is the youngest person in human history relative to his birth date because he traveled through space-time along a different path than the rest of us. Think about what this means for interstellar missions to other stars. Even with advanced propulsion, reaching another star system will take decades at minimum, and more likely centuries unless we can achieve velocities close to the speed of light. For generation ship spacecraft, where multiple generations are born, live, and die during the journey, time dilation becomes a crucial factor in mission planning. If the ship travels at a significant fraction of light speed, the travelers will age less than Earth does. A journey that takes 100 years from Earth's perspective might take only 50 years for the travelers at 87% light speed. The generation ship arrives with fewer generations having passed on board than would have passed on Earth. This affects everything: how many people to send, how much food and resources are needed, how to structure society on board. But here's the catch: to achieve these speeds, you need enormous amounts of energy. Accelerating even a small spacecraft to a significant fraction of light speed requires energy scales we currently can't achieve. And the faster you go, the more energy you need. This is one of the great challenges of interstellar travel, not just the time it takes, but the energy required to make time dilation work in your favor. Let's return to a more immediate question. What about astronauts who spend extended time on the International Space Station or future lunar bases? How do they experience time differently? The answer is, they don't notice it subjectively. Time feels normal to them, but their clocks and their bodies are aging at a different rate than people on Earth. This has practical implications. Medical treatments, medication dosages, biological experiments, all of these are calibrated based on time. If time is flowing differently, even by milliseconds, experiments might yield slightly different results. Scientists conducting long-term studies on the ISS must account for this. It's a small correction, but in precision science, small corrections matter. Have you ever wondered what it would feel like to come back to Earth after years in space knowing you've aged less than everyone else? Knowing that while you were gone, a tiny but real amount of time passed for them that didn't pass for you. It's a strange thought. Being chronologically younger than your birth date suggests living proof that time is not absolute. And here's something even stranger to consider. If we ever develop the technology to travel at speeds close to light, astronauts could journey to distant stars and return to Earth having aged only decades, while centuries or millennia pass on Earth. They would be time travelers not to the past, but to the future. They could leave Earth in the 22nd century and return in the 25th century, biologically only 40 years older. Everyone they knew would be gone. Society would have transformed. They'd be visitors from the past, arriving in a world they can barely recognize. This is one-way time travel, and it's possible, not theoretically possible, but actually possible under the laws of physics as we understand them. This is the profound reality of the aging astronaut effect. It's not just a curiosity, it's a fundamental aspect of space exploration. Every journey into space is a journey through time. Every astronaut who leaves Earth is making a choice consciously, or not to live in a slightly different temporal stream than the rest of humanity. And as we venture farther and faster, these choices become more significant. The universe is offering us a gift, the ability to age less to experience less time, to jump forward into the future. But the price is separation from the people we love, from the world we know from the shared timeline of human history. As we prepare to become a spacefaring species, we need to grapple with these realities. Time dilation is not a problem to be solved. It's a feature of the universe, and we must learn to navigate it just as sailors once learned to navigate the oceans. And the deeper we venture into the cosmos, the more we'll discover about the flexible, strange, and beautiful nature of time itself. But what if we could use time dilation not just as a side effect, but as a tool? What if we could deliberately travel through time using the curvature of space-time to leap into the future? That possibility and its limitations reveals something fundamental about the structure of reality and the boundaries of what's possible. Imagine stepping into a spacecraft and accelerating to nearly the speed of light. You travel for what feels like 10 years of your life, your experiences, your aging. Then you turn around and return to Earth. When you step off the ship, you discover that 1,000 years have passed. Everyone you knew is gone. Civilizations have risen and fallen. Technology has transformed beyond recognition. You've journeyed through time not by bending the rules of physics, but by following them. You've become a time traveler leaping forward through the centuries while barely aging. This isn't science fiction. This is a real possibility permitted by the laws of relativity. Time travel to the future is not only possible, it's inevitable for anyone who moves fast enough. But there's a catch. It's a one-way ticket. You can go forward in time, but you can never go back. And understanding why reveals something profound about the structure of causality and the nature of the universe itself. Let's start with the basic principle. Time dilation allows you to experience less time than the rest of the universe. The faster you move through space, the slower you move through time. This isn't a trick or a loophole. It's a direct consequence of how space-time is structured. At everyday speeds, the effect is tiny. But as you approach the speed of light, time dilation becomes extreme. At 99.9%, the speed of light time slows down by a factor of about 22. 1 year for you equals 22 years for someone stationary at 99.99% light speed. The factor jumps to 71. At 99.999%, it's 224. The closer you get to light speed, the more dramatic the effect. This means that if you could build a spacecraft capable of reaching speeds close to light, you could use it as a time machine. Not a machine that transports you through time instantaneously, but one that lets you skip forward through time by aging less than the universe around you. Physicists sometimes call this the twin paradox time machine. And it's the only form of time travel that's unambiguously allowed by the known laws of physics. Here's a concrete example. Suppose we build a spaceship capable of constant acceleration at 1g, the same acceleration you feel from Earth's gravity. This keeps the astronauts comfortable, experiencing normal weight throughout the journey. If this ship accelerates at 1g for about 1 year of ship time, it will reach speeds close to the speed of light. If it continues accelerating, approaching, but never quite reaching light speed, the time dilation effects become enormous. Calculations show that with this constant 1-gram acceleration, astronauts could reach the Andromeda Galaxy 2.5 million light-years away in only about 28 years of ship time. From Earth's perspective, more than 2.5 million years would pass. The astronauts would arrive at Andromeda having aged only 28 years, but Earth and everyone on it would be long gone, lost to the deep future. This isn't speculation. The mathematics is solid based on Einstein's special relativity. The challenge isn't the physics, it's the engineering. To accelerate a spacecraft to near light speed requires staggering amounts of energy. With chemical rockets, it's impossible. With nuclear propulsion, it's barely conceivable. Some physicists have proposed antimatter engines, where matter and antimatter annihilate each other, converting mass directly into energy with 100% efficiency. Even with antimatter, you'd need vast quantities of fuel. For a ship massing just a few tons to reach 90% light speed, you'd need roughly as much energy as the entire world uses in a year. It's an almost insurmountable barrier with current or near-future technology. But let's imagine we solve the energy problem. Suppose we develop fusion drives, matter-antimatter engines, or some breakthrough propulsion system that can accelerate ships to relativistic speeds. What then? What does time travel to the future look like in practice? First, understand that from the traveler's perspective, the journey feels normal. You don't experience time moving slowly. Your heartbeat feels regular. Your thoughts proceed at their usual pace. It's only when you look outside at the universe rushing past that you notice something strange. Stars seem to shift in color due to relativistic Doppler effects. Light from ahead, blue shifts. Light from behind, red shifts. The visible universe appears distorted, compressed, forward into a smaller cone of vision. These are the optical effects of traveling near light speed, and they'd be both beautiful and disorienting. As you travel time, on Earth speeds forward. If you could somehow watch a clock on Earth, which you can in real time due to signal delays, you'd see it ticking faster and faster as your velocity increases. The Earth would age before your eyes. Decades then, centuries then, millennia would pass. There while only years pass for you. When you arrive at your destination and decelerate, you step into a future Earth that's moved on without you. This is the essence of one-way time travel. You can visit the future, but the act of traveling makes it impossible to return to your own time. Now, why can't you travel backward in time? Why is time travel to the past forbidden? The answer lies in causality. The principle that causes must precede their effects. If you could travel backward in time, you could theoretically create paradoxes. The most famous is the grandfather paradox. If you go back in time and prevent your grandparents from meeting, you would never be born. But if you're never born, you can't go back in time to prevent them from meeting. It's a logical contradiction. For decades, physicists debated whether the laws of physics permit such paradoxes or whether there's some mechanism that prevents them. General relativity. Einstein's theory of gravity does allow certain solutions, certain configurations of space-time that include closed time-like curves. These are paths through space-time that loop back on themselves, theoretically allowing you to return to your own past. The most famous example is the Gödel universe, a rotating universe solution found by mathematician Kurt Gödel in 1949. In Gödel's model, if you travel far enough in one direction, you eventually return to your own past. Another example is the Tipler cylinder, an infinitely long, rapidly rotating cylinder of matter that warps space-time around it, creating closed time-like curves. And then there are wormholes, hypothetical tunnels through space-time that could in principle connect different points in time as well as space. But here's the problem: all of these solutions require exotic conditions that probably don't exist in our universe. The Gödel universe doesn't match the universe we observe. Ours isn't rotating in the right way. The Tipler cylinder requires infinite length and rotation speeds that might not be physically possible. Wormholes, if they exist at all, would require exotic matter with negative energy density to keep them open, and we have no evidence that such matter can exist in the quantities needed. Moreover, even if you could create a wormhole, physicist Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel to the past. Quantum effects, he argued, would cause any closed time-like curve to become unstable and collapse before it could be used. It's as if the universe has a built-in defense mechanism against paradoxes. So, the consensus among physicists is that while forward time travel is not only possible, but inevitable at high speeds, backward time travel is almost certainly impossible. The laws of physics seem to permit one-way journeys into the future, but forbid returns to the past. You can leap forward, but you can never leap back. Here's a thought experiment to illustrate why this matters. Suppose you board a ship traveling at 99.9% light speed and journey to a star 1,000 light years away. From Earth's perspective, the journey takes about 1,000 years. From your perspective, time dilation compresses the journey to about 45 years. You arrive at the star, spend a few years exploring, then return at the same speed. Another 45 years for you, another 1,000 years for Earth. When you land, you've aged 90 years, but Earth has aged 2,000 years. You left in, say, 2,100 and returned in 4,100. You've traveled 2,000 years into Earth's future. Everyone you knew is dead. History has unfolded in ways you can't predict. You're a visitor from the past, arriving in a world you helped leave behind but can never return to. This creates profound emotional and philosophical questions. Would you take that journey knowing you can never go back? Knowing that Earth might have solved all its problems or destroyed itself in your absence? Some physicists have speculated that this is why we haven't encountered time travelers from the future. Perhaps civilizations that develop such technology choose not to use it, recognizing the irreversible severing of ties with their own time. Or perhaps the energy requirements are so immense that no civilization ever achieves it. But there's another approach to forward time travel that doesn't require near-light speeds: gravitational time dilation. Remember, time moves more slowly in strong gravitational fields. If you could position yourself near a massive object, say, orbiting close to a black hole's event horizon, you'd experience extreme time dilation. For every hour you spend there, decades or centuries could pass in the wider universe. When you leave and return to normal space, you'd have traveled into the future. The 2014 film Interstellar depicted this. The crew visits a planet orbiting near a black hole, where 1 hour equals 7 years elsewhere. When they return to their ship, their colleague has aged decades. This scenario is physically plausible, though it requires surviving the intense tidal forces and radiation near a black hole. The advantage of gravitational time dilation is that you don't need to accelerate to extreme velocities. You just need to position yourself in a deep gravitational well. The disadvantage is finding such a well that won't kill you. Black holes are dangerous. Neutron stars are dangerous. White dwarfs might be survivable if you orbit at a safe distance, but the time dilation effects are much weaker. Still, in principle, you could use gravity as a time machine, hovering near a massive object to let the universe age around you before returning to explore the future. Here's a common mistake people make. When thinking about time travel, they confuse time dilation with slow motion. They imagine astronauts moving sluggishly, their voices deep in their actions, lethargic. That's not how it works. If you're experiencing time dilation, you feel completely normal. Your clock ticks at its usual rate from your perspective. Your heart beats normally. Your thoughts flow at their regular pace. The dilation is only apparent when you compare your clock to someone else's in a different reference frame. Time dilation is a relational effect, not an experiential one. Another misconception. People think that because you can travel forward in time, there must be some symmetry that allows backward travel. But the universe isn't symmetric in this way. The laws of thermodynamics give time a direction, entropy increases, disorder spreads. And this defines an arrow of time pointing from past to future. You can surf along this arrow, speeding through it by experiencing less time yourself, but you can't reverse it. The arrow of time is a one-way street, and relativity doesn't change that. Let's consider some creative proposals physicists have made for forward time travel. One idea is the generation ship, which we touched on earlier. Instead of reaching high speeds, you build a massive ship designed to sustain a population for centuries or millennia. The ship travels at moderate speeds, say 10% light speed, so time dilation is mild. Generations are born, live, and die during the journey. From the traveler's perspective, the journey might take 500 years. From Earth's perspective, it takes 550 years. When the ship arrives at its destination, star system, the descendants of the original crew step out into a future that's only a bit farther ahead than the journey itself. This isn't dramatic time travel, but it is temporal displacement. The travelers have lived through 500 years, while their home world has experienced 550. Another proposal is the wait and return strategy. Send a probe to a distant star at high velocity. By the time it arrives, centuries have passed on Earth. Technology has advanced. A faster ship is built and sent to catch up. It overtakes the first probe reaching the star in less time from Earth's perspective, though the travelers on the faster ship experience less subjective time. By leapfrogging missions, humanity could explore distant stars, while using time dilation to minimize the subjective cost to explorers. Do you ever wonder if future humans, thousands of years from now, might look back on our time as impossibly distant? That's what time dilation does. It allows individuals to skip forward over that gulf, to bridge centuries or millennia in a single lifetime. It's not immortality, but it's something close temporal displacement that lets you outlive your era. Here's the deepest truth about time travel. The universe allows it, but only in one direction. The laws of physics open a door to the future and firmly close the door to the past. This asymmetry isn't arbitrary. It's built into the structure of causality entropy and the arrow of time. Forward time travel is a consequence of relativity. Backward time travel would require violations of causality that the universe seems designed to prevent. We live in a cosmos that lets you leap forward through time, but never lets you return to where or when you started. So, if humanity ever achieves the technology to travel at relativistic speeds, we'll face a choice. We can send explorers to distant stars, knowing they will arrive in a future Earth they can never return to. We can use time dilation as a tool for exploration, but we must accept the cost separation from our own time, our own people, our own era. Time travel to the future is possible, but it's also irreversible, and that irreversibility shapes what it means. And this brings us to the final question. What does all of this time dilation relativity, the flexibility of time, mean for humanity's future? How do we live in a universe where time itself bends and flows? What does it mean to be human, when time is no longer a shared universal experience, but a personal journey shaped by gravity and motion? Imagine waking up one morning on a space station orbiting Mars. You check the time, it's 8:00 a.m. by your clock. You send a message to your family on Earth, "Good morning, hope you're doing well." You wait for their reply. When it comes, they say, "Good morning back," but their clock shows 8:03 a.m. Not because of signal delay, you've already accounted for that, but because time itself is flowing at different rates on Mars and Earth. Your now and their now are no longer the same. You're living in parallel time streams, separated not by distance alone, but by the fundamental architecture of space-time. This is the future we're stepping into, a future where humanity is scattered across worlds, each one ticking to its own rhythm, each population aging at its own pace. This is what it means to live in Einstein's universe. For most of human history, time was the one thing everyone shared. No matter where you were, on a mountaintop, in a valley, on a ship at sea, a second was a second, an hour was an hour, a year was a year. Time was the universal backdrop against which all of life unfolded. But Einstein shattered that illusion. He revealed that time is not universal, it's local, it's personal. It bends with gravity, stretches with speed, and varies from place to place. And now, as we prepare to become a spacefaring species, we must learn to live with this truth. The implications are staggering. When humans establish a permanent base on the moon, as NASA plans to do within the next decade, lunar residents will experience time flowing about 56 microseconds faster per day than people on Earth. Over a year, that's about 20 milliseconds. It sounds negligible, and for day-to-day life, it is. But for precision operations, navigation, communication, scientific experiments, it matters. Engineers are already designing lunar timekeeping systems to account for this. The Lunar Time Standard, currently in development, will define how time is measured on the moon and how it translates to Earth time. It's not just a technical problem, it's a philosophical shift. We're acknowledging that the moon and Earth exist in different temporal frameworks, and we need infrastructure to bridge them. Mars is even more complex. A Martian day, a sol, is about 24 hours and 37 minutes long, so Martian colonists will likely adopt a Martian calendar. But beyond that time, on Mars flows faster than on Earth due to Mars's weaker gravity. The difference is small, 0.3 milliseconds per day, but it accumulates. Over decades, Martian colonists and Earth residents will drift apart temporally. A child born on Mars in 2050 and a child born on Earth on the same day will by 2010 have experienced slightly different amounts of time. The Martian child will be about 5.5 seconds older biologically and temporally. It's a tiny difference, but it's real. These two humans born on the same date will have lived through different durations of existence. Their ages won't quite match. Now scale this up. Imagine humanity spread across the solar system on the moon. Mars, the moons of Jupiter and Saturn, space stations in various orbits and ships traveling between them. Each location has its own gravitational time dilation. Each ship has its own velocity time dilation. There is no longer a single human timeline. There are dozens, hundreds, perhaps thousands of timelines, all running at slightly different rates, all valid, all real. We'll need protocols for synchronizing clocks across these timelines. We'll need to agree on a reference frame, perhaps, solar system barycentric time, which measures time relative to the center of mass of the entire solar system. But even then, each location will need to translate that reference time into its local time, accounting for its unique position in the gravitational landscape and its motion through space. This fragmentation of time has profound social implications. Think about communication. If you're on Earth and you call someone on Mars, there's already a signal delay between 4 and 24 minutes, depending on the planet's positions. But there's also a time dilation difference. When you say, "It's 3 p.m. here," that statement has to be translated into Martian time, accounting for both the different day length and the different flow of time. Coordinating activities across worlds becomes a challenge not just of distance, but of temporal reference frames. Business meetings, family gatherings, scientific collaborations, all of these will require careful attention to whose clock we're using and how we're translating between time streams. And what about cultural identity? On Earth, we have always defined ourselves partly by time. We share historical moments, wars, discoveries, celebrations that happen at the same time for everyone. But in a multi-world civilization, that shared temporality breaks down. An event happening now on Earth is not happening now on Mars in any absolute sense. Simultaneity becomes relative. History becomes fragmented across reference frames. Future historians will have to specify not just when something happened, but in which reference frame: Earth time, Mars time, lunar time, ship time. The very concept of the year 2100 will have different meanings depending on where you are. Let's talk about long-term missions. Suppose we send astronauts on a round-trip journey to Jupiter's moons, a mission that takes, say, 10 years. During those 10 years, the astronauts are traveling at high velocity and spending time in different gravitational fields. They'll age slightly less than people on Earth, maybe a few seconds less, over the course of the mission. When they return, they'll be biologically younger than their peers who stayed behind. It's a small difference, but it's measurable. Now, imagine doing this repeatedly. Some people become career astronauts, spending most of their lives in space accumulating these small time dilation effects. Over a 40-year career, they might age 10 or 20 seconds less than their Earthbound contemporaries. They become the youngest people of their generation, literally living proof that time is flexible. This raises ethical and social questions. In a future where some people age more slowly than others due to their career choices, do we need to rethink how we measure age, retirement, life expectancy? If two people are born on the same day, but one becomes a deep space astronaut and the other stays on Earth, they will age at different rates. By their 80th birthday, by whose clock, they might differ in biological age by a minute or more. It's still small, but it's a departure from the assumption that everyone born on the same day is the same age. Now consider interstellar missions the ultimate expression of time dilation. If we ever develop propulsion systems capable of reaching significant fractions of light speed, we could send explorers to nearby stars. A mission to Proxima Centauri, 4.24 light-years away at 80% light speed, would take about 5.3 years from Earth's perspective. But for the astronauts' onboard time, dilation would compress the experience to about 3.2 years. They'd arrive having aged 3.2 years, while Earth aged 5.3 years. On the return journey, the same thing happens. Total mission time, from Earth's perspective, about 11 years. Total mission time for the astronauts, about 6.4 years. The astronauts return nearly 5 years younger, biologically, than they should be. They've traveled not just through space, but through time, skipping over almost 5 years of Earth's history. And if we push the speeds higher, the effects become dramatic. At 99% light speed, a journey to a star, 50 light-years away, takes about 50 years from Earth's perspective, but only about 7 years for the travelers. At 99.9% light speed, a journey across the galaxy, 100,000 light-years, could take only about 450 years for the travelers, while 100,000 years pass on Earth. The travelers would arrive in a future where Earth is unimaginably different, where humanity might have evolved, spread, or even vanished. They'd be emissaries from a distant past, arriving in a cosmos that has moved on without them. This is both the promise and the peril of relativistic travel. Time dilation allows us to cross vast distances within a human lifetime, the traveler's lifetime. But it severs us from our own time. We can reach the stars, but we can never go home, not to the home we left anyway. We become unstuck in time, wandering through the future as visitors from the past. Do you ever think about what it would mean to outlive your entire civilization? Not by living longer, but by moving faster. To return from a journey and find that everyone you knew, everything you remembered, has been swept away by the river of time. But let's bring this back to the present. Right now in 2026, time dilation is already part of our daily lives. Every time you use GPS, your phone is correcting for relativistic effects, accounting for the fact that satellites experience time differently than you do. Every time a particle accelerator operates, engineers are calculating time dilation for particles moving at near light speed. Every astronaut who returns from the International Space Station has aged microseconds less than they would have on Earth. Relativity isn't abstract theory, it's operational reality, and it's shaping how we plan the future. NASA's Artemis program, which aims to return humans to the moon, includes provisions for lunar timekeeping. The European Space Agency is studying how to synchronize clocks across cislunar space, the region between Earth and the Moon. SpaceX's plans for Mars colonization will eventually require Martian time standards. The James Webb Space Telescope, orbiting at a point in space where Earth's and the Sun's gravity balance, experiences a unique time dilation and profile that must be accounted for in its observations. We're building infrastructure for a future where time is not uniform, where every mission, every habitat, every spacecraft operates in its own temporal context. Here's what's beautiful about this. We're learning to navigate space-time, not just space. For millennia, humans explored the surface of Earth, mapping continents and oceans. Then we ventured into space, mapping planets and stars. Now we're learning to map time itself, to understand how it flows differently in different places, to build systems that can translate between temporal reference frames, to live with the reality that the universe doesn't have a single clock. We're becoming a civilization that understands time as a dimension, a landscape with hills and valleys, fast-flowing regions, and slow-moving eddies. And just as sailors once learned to navigate by the stars, we're learning to navigate by the curvature of space-time. This is Einstein's true legacy. He didn't just give us equations, he gave us a new way of seeing the universe. He showed us that time is not a rigid framework imposed from outside, but a flexible fabric woven into the very structure of reality. He revealed that every clock, every heartbeat, every moment of existence is shaped by gravity and motion, by where you are and how you're moving. And he showed us that the universe is richer, stranger, and more beautiful than we ever imagined. As we stand on the threshold of becoming a multi-world species, we carry this knowledge with us. We know that the moon ages faster than Earth. We know that astronauts return younger. We know that clocks in orbit tick at different rates than clocks on the ground. We know that time is not absolute, that now is local, that the universe doesn't care about our human need for simultaneity. And we're learning to live with that. We're building technologies that translate between time streams. We're designing missions that account for relativistic effects. We're preparing for a future where humanity is scattered across dozens of worlds, each one living in its own temporal rhythm, and yet still connected by the shared knowledge that we all inhabit the same space-time, just at different points within it. This is what it means to live in Einstein's universe. It means accepting that time is not what we thought it was. It means embracing the flexibility of moments, the relativity of now the curvature of space-time. It means understanding that every journey changes, not just where you are, but when you are. And it means recognizing that the most precious thing we have, time itself, is not a universal constant, but a personal experience unique to each path through the cosmos. So, when you look up at the night sky, remember every star, every planet, every galaxy is ticking to its own rhythm. Time flows differently out there than it does here. And someday when humans walk on distant worlds or travel to faraway stars, they'll carry with them the knowledge that time is not their enemy, but their companion, flexible fluid, and forever intertwined with the journey they choose to take. The clock that changed everything in 1971 didn't just prove Einstein right. It opened a door to understanding the universe in a completely new way. It showed us that time is part of the adventure, not separate from it. And as we venture into the cosmos, we take that understanding with us, navigating not just through space, but through the beautiful, intricate, ever-changing landscape of time itself. Thank you for joining me on this journey through the nature of time. I hope it's expanded your sense of what's possible, what's real, and what it means to exist in a universe where every moment is shaped by the fabric of space-time. If you enjoyed this exploration, please like and subscribe. It helps us continue creating these journeys into the mysteries of science. And stay tuned, because there are so many more wonders waiting to be discovered, so many more stories the universe is eager to tell. Until next time, may your moments be many, and may you cherish each one, knowing now just how extraordinary time truly is. Sleep well and dream of the stars.